The universe stretches out before us, an endless sea of stars, planets, and mysteries that defy explanation. Look up at the night sky, and what you see is just a fraction of what's out there. Hidden in the darkness are enigmas so strange, so baffling, that even the brightest minds in science are left scratching their heads. From objects that move in ways physics says they shouldn't, to signals from the void that hint at something we can't yet understand, space is filled with anomalies that challenge everything we think we know. And today, we're diving deep into the 25 most mind-bending cosmic puzzles that continue to leave experts in awe. Imagine a place where the rules of reality seem to bend, where light behaves strangely, where entire galaxies vanish without a trace, and where whispers from the cosmos suggest forces beyond our current comprehension. These aren't plot points from a science fiction novel. They're real phenomena happening right now in the vast expanse above us. Some of these mysteries have lingered for decades, resisting every attempt to solve them. Others have only recently come to light, sparking debates and theories that push the boundaries of human knowledge. Whether it's a star that flickers in ways no star should, or a region of space so eerily empty it defies logic, each of these anomalies holds a clue to the universe's deepest secrets. This isn't just a list, it's a journey into the unknown, a chance to explore the edges of our understanding, where the answers we seek might rewrite textbooks or even reveal entirely new chapters in science. As we uncover these cosmic oddities one by one, you'll find yourself questioning what's possible, marveling at the sheer scale of what we don't yet know, and maybe even feeling that same spark of curiosity that drives astronomers and physicists to keep searching. So let's set off together into the great unknown where the universe's most perplexing mysteries await. By the end, you might just see the night sky a little differently, not just as a collection of stars, but as a canvas for the inexplicable, the bizarre, and the utterly extraordinary. One of the most tantalizing mysteries in the search for extraterrestrial intelligence began on a quiet August night in 1977. The Big Ear radio telescope, sweeping the skies for distant signals, picked up something extraordinary, a burst of radio waves so powerful, so strikingly artificial in nature that an astronomer scrawled, "Wow." In red ink on the printout, that single word would give this enigma its name. Lasting exactly 72 seconds, the signal came from the direction of the constellation Sagittarius, matching the expected frequency range of potential alien transmissions. And then, just as suddenly as it appeared, it vanished, never to be heard again. Decades later, the WOW signal remains a cosmic riddle. Some scientists argue it could have been a natural phenomenon, a freak burst from a comet, or an unknown astrophysical event. Others point to its narrow frequency band, a hallmark of engineered communication, as evidence it might have been something more. The signal's intensity spiked and faded exactly as expected if it originated from a distant source passing through the telescope's field of view, adding to its eerie precision. Despite exhaustive searches, no repeat signal has ever been detected in the same region of space, deepening the mystery. What makes this anomaly so compelling isn't just the unanswered question of its origin. It's the possibility, however slim, that for 72 seconds we might have eavesdropped on another civilization reaching out across the cosmos. Imagine the implications, a fleeting whisper from the void, hinting that we're not alone. Until another signal like it appears, the WOW event stands as both a beacon of hope and a frustrating dead end in humanity's quest to answer one of our oldest questions: are we the only ones out there? While skeptics and believers continue to debate, one thing is certain: that brief burst of radio waves rewrote the conversation about extraterrestrial life. It proved that the universe is capable of surprises, of phenomena we can't yet explain. And perhaps that's the real lesson of the WOW signal, not just that the truth may be out there, but that the cosmos is far stranger, far more unpredictable than we ever imagined. Some stars behave exactly as we expect, steady, predictable, and bound by the laws of physics. Then there's Tabby's star, a cosmic rebel that refuses to play by the rules. Officially known as KIC 8462852, this distant sun, roughly 1,400 light-years away in the constellation Cygnus, behaves like nothing else we've ever observed. Most stars dim slightly when planets pass in front of them, a predictable, rhythmic flicker, but Tabby's star doesn't just dim, it plunges into darkness irregularly, sometimes dropping in brightness by a staggering 22%. That's not a gentle shadow. It's as if something massive and unpredictable is blocking its light over and over with no discernible pattern. When astronomers first spotted this oddity in data from the Kepler Space Telescope, they scrambled for explanations. Initial theories pointed to a swarm of comets or a thick cloud of planetary debris, but even those couldn't account for the sheer scale and irregularity of the dimming. Then came the more radical idea: could this be evidence of an alien megastructure? The notion wasn't pure science fiction. Physicists have long theorized about Dyson spheres, hypothetical constructs advanced civilizations might build to harness a star's energy. If such a structure were partially built or uneven, it could explain the bizarre light patterns. But before we jump to extraterrestrial conclusions, other possibilities linger. Some researchers argue for an interstellar dust cloud, dense and clumpy, drifting between us and the star. Others suggest that Tabby's star might have recently devoured a planet, leaving behind a chaotic debris field. The problem: no single theory fits all the data perfectly. Even years of observation and analysis haven't cracked the case. What makes Tabby's star so fascinating isn't just its strangeness, it's the humbling reminder that the universe still holds phenomena we can't yet explain. Whether it's undiscovered astrophysics, an unprecedented cosmic event, or something even more extraordinary, this star challenges our assumptions at every turn. And that's the beauty of it. In the vastness of space, anomalies like Tabby's star keep us questioning, searching, and marveling at just how much we still have to learn. High above our planet, hidden in the swirling dance of space debris and satellites, lurks a legend that has gripped conspiracy theorists and space enthusiasts for decades: the Black Knight satellite. Stories tell of an ancient alien object silently orbiting Earth, observing humanity for thousands of years. Some claim it's a relic from an advanced extraterrestrial civilization, while others insist it's a piece of lost human technology, far older than anything we've launched. But where does the myth end and reality begin? The tale of the Black Knight first gained traction in the 1950s, when newspapers reported strange radio signals supposedly intercepted by researchers. Then, in 1960, the US Air Force supposedly detected a mysterious dark object in polar orbit, an unusual path for satellites at the time. Images from early space missions, like the 1998 Endeavour shuttle flight, added fuel to the fire when blurry photographs appeared to show a bizarre, angular shape against the blackness of space. UFO communities latched onto these fragments, weaving them into a narrative of extraterrestrial surveillance. But science tells a different story. Astronomers point out that many so-called Black Knight sightings can be explained as misidentified space debris, discarded rocket parts, thermal blankets, or even fragments from old satellites. The signals reported in the 50s, likely natural radio waves or early satellite interference. As for those enigmatic photos, they often capture known objects like detached insulation or other mundane artifacts of human spaceflight, distorted by shadows and camera angles. Yet what makes the Black Knight enduring isn't just the mystery, it's the deeper question it forces us to confront. Why do we yearn for hidden truths in the cosmos? Perhaps the legend persists because it taps into something primal, the thrill of the unknown, the fear of being watched, or the hope that we're not alone in the universe. For every skeptic dissecting the evidence, there's a dreamer who wonders what if, just this once, the myth were real. So while the Black Knight may not be an alien sentinel, its story still holds power. It reminds us that space is more than just physics and data. It's a canvas for our imagination where reality and myth collide in the endless dark, and who knows? Maybe one day humanity will find its own version of the Black Knight out there, not as a phantom from conspiracy lore, but as proof that the universe is stranger than fiction. In the vast emptiness between stars, most objects follow the predictable rules of gravity until one didn't. In October 2017, astronomers spotted something extraordinary racing through our solar system. It wasn't from here, it wasn't even from our cosmic neighborhood. This strange visitor, named Oumuamua Hawaiian for Scout, was the first confirmed interstellar object ever detected passing through our celestial backyard. But what made it truly remarkable wasn't just its origin. It defied expectations at every turn. For starters, Oumuamua didn't look like anything we'd seen before. Most asteroids and comets are roughly spherical or lumpy, but this object was elongated. Some estimates suggested it was up to 10 times longer than it was wide, tumbling end over end like a cosmic cigar. Then there was its movement. As it hurtled away from the sun, instead of slowing down as expected, it sped up slightly, as if something were pushing it. Comets often accelerate like this when their icy surfaces vaporize, creating a visible tail. But Oumuamua had no tail, no detectable gas or dust, no obvious explanation for its sudden burst of speed. The scientific community erupted with theories. Some proposed it was a rare type of dark comet, a body that vents invisible hydrogen gas as it heats up. Others suggested more exotic possibilities, fragments of a shattered planet, a porous iceberg made of molecular hydrogen, or even an artifact of alien technology. Harvard astronomer Avi Loeb famously floated the idea that Oumuamua could be a light sail, a thin, artificial structure propelled by starlight. While most researchers remained skeptical of extraterrestrial origins, the debate highlighted just how puzzling this object was. What makes Oumuamua so captivating isn't just the mystery of its true nature, it's the realization that our solar system isn't isolated. The universe is constantly flinging material across the void, and until now, we'd never caught one in the act. Every unusual trait of this interstellar traveler offers a clue about how other star systems form and behave. Was it a rare oddity, or are such objects common, slipping past us unnoticed? As Oumuamua faded from view, it left behind more questions than answers, but its brief visit changed astronomy forever. It proved that interstellar visitors are real, that our detection methods are improving, and that space still has the power to surprise us. The next time an outsider streaks through our solar system, we'll be watching, ready to uncover even more of the universe's untold secrets. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars, many of which host planets in the so-called Goldilocks zone, where life could theoretically thrive. Given these odds, the cosmos should be teeming with civilizations, their signals filling the void. Yet when we listen, all we hear is silence. This glaring contradiction is the heart of the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody? If intelligent life is likely, why does the universe seem so empty?" One unsettling possibility is the Great Filter, a hypothetical barrier that prevents life from advancing to interstellar levels. The theory suggests that somewhere between the emergence of life and the colonization of galaxies, there's a step so difficult, so unlikely, that almost no species surpasses it. The filter might lie in our past. Perhaps the leap from simple cells to complex life is rarer than we think, or worse, it could await us in the future. If advanced civilizations inevitably destroy themselves through war, environmental collapse, or unchecked technology, humanity might be heading toward the same dead end. Then there's the zoo hypothesis, the idea that extraterrestrial societies consciously avoid contact, observing us like animals in a cosmic preserve. Maybe they're waiting for us to reach a certain level of maturity, or they've imposed ethical guidelines against interfering with developing worlds. It's a comforting thought, but it raises another question. If an advanced civilization exists, could every member resist the urge to make contact forever? Other theories paint a lonelier picture. We might simply be the first arriving early in a universe that's still young, with intelligent life yet to emerge elsewhere. Or perhaps interstellar travel is impossible, with the vast distances between stars acting as an unbreakable prison. Some argue that advanced life forms may have transcended physical existence, uploading their consciousness into digital realms we can't detect. Whatever the answer, the Fermi paradox forces us to confront our place in the universe. Are we a fluke, a doomed experiment, or just one voice in a chorus we can't yet hear? Every silent radio dish, every empty exoplanet scan deepens the mystery. But maybe that's the point, not to despair, but to keep searching. Because if the universe teaches us anything, it's that the truth is often stranger and more wondrous than anything we've imagined. At the very edges of our observable universe, something strange is happening. A cosmic tug of war that shouldn't exist. Galaxy clusters, massive collections of stars and dark matter, are all moving in the same direction at inexplicable speeds. This phenomenon, dubbed dark flow, suggests an unseen force is pulling them toward a point beyond the known cosmos. It's as if the universe itself is being drawn toward something immense, something we can't see or even comprehend. When scientists first detected this motion in 2008, it sent shockwaves through the astrophysics community. These clusters weren't just drifting randomly. They were racing toward a specific region of space at over 2 million miles per hour. The oddest part, there's nothing in that direction, no supercluster, no dense concentration of matter, nothing visible to explain the pull. Dark flow defies the fundamental principle that the universe's matter should be distributed evenly on large scales. So what could possibly be yanking entire galaxies off course? One radical theory points to the influence of other universes. In the multiverse hypothesis, our cosmos might be just one bubble in an infinite sea of universes, each with its own physical laws. If a neighboring universe happened to brush against ours, its gravity could create the mysterious pull we observe as dark flow. It's a mind-bending idea, evidence of another reality leaking into our own. Others argue for an equally strange explanation, a colossal, unseen structure beyond our observational horizon. Imagine a supermassive knot of matter so distant that its light hasn't had time to reach us, yet its gravitational grip extends far enough to drag galaxies toward it. This would mean the universe is far lumpier, far less uniform than we ever imagined. Or perhaps dark flow is a phantom, an illusion caused by imperfections in our measurements or gaps in our understanding of gravity itself. Some researchers suggest that Einstein's theory of relativity might need tweaking on cosmic scales, that we're missing a piece of the puzzle that would make sense of this enigma. What makes dark flow so captivating isn't just the mystery, it's what it represents. If real, it hints at realms beyond our perception, at forces shaping the cosmos in ways we're only beginning to glimpse. Whether it's proof of parallel universes, hidden megastructures, or new physics, one thing is clear: the universe still holds secrets that challenge everything we think we know. And that's the thrill of it. Every anomaly like dark flow isn't just a question mark. It's an invitation to look deeper, to push further, and to wonder what else might be out there, waiting to rewrite the story of existence itself. Somewhere in the depths of space, hidden behind the thick veil of stars, dust, and gas that makes up our own Milky Way, lies a gravitational mystery so powerful it's bending the motion of hundreds of thousands of galaxies. Scientists call it the Great Attractor, an enigmatic region of space roughly 250 million light-years away that's pulling entire galaxy clusters, including our own, toward it with irresistible force. This isn't just a gentle nudge. The local group, which includes the Milky Way and Andromeda, is racing toward it at over 1,000,000 miles per hour. Yet for decades, the Great Attractor remained one of the universe's best-kept secrets, obscured by what astronomers call the zone of avoidance, the dense band of our galaxy's own material that blocks our view of what lies beyond. Studying this cosmic heavyweight has been like trying to decipher a message through a fogged-up window. Traditional optical telescopes can't pierce the Milky Way's dusty plane, leaving scientists to rely on instruments that detect radio waves and X-rays, wavelengths that can slip through the cosmic clutter. What they've uncovered is both fascinating and puzzling. The Great Attractor isn't just a single massive object, but an immense concentration of matter, likely a supercluster of galaxies so dense that its gravity dominates an entire region of space. Yet even this doesn't fully explain its pull. There's something else lurking in the shadows, something even larger. Enter the Laniakea supercluster, a mind-bending structure spanning 500 million light-years, revealed in 2014. Our Milky Way, it turns out, is just a tiny speck on the outskirts of this vast cosmic web, with the Great Attractor acting as its gravitational heart. But here's the twist: the Great Attractor itself seems to be moving, pulled toward something even more massive in the distant Shapley supercluster. It's as if the universe is built like a set of Russian nesting dolls, each layer revealing a deeper, more complex hierarchy of gravitational influence. The implications ripple far beyond mere curiosity. If the Great Attractor and structures like it are shaping the large-scale flow of galaxies, it challenges our understanding of cosmic evolution. According to standard models, the universe's matter should be distributed relatively evenly after the Big Bang. Yet these immense concentrations suggest something else, clumping on scales we're only beginning to map. Some scientists speculate that dark matter, the invisible glue holding the cosmos together, might be clustered in ways we don't yet comprehend. Others wonder if our models of gravity itself need revising on the largest scales. What makes the Great Attractor so compelling isn't just its hidden nature, it's the way it forces us to confront the limits of our knowledge. Every breakthrough peels back another layer, revealing how much we still don't understand about the universe's grand architecture. And that's the thrill of the hunt. As new telescopes and technologies pierce the zone of avoidance, who knows what other cosmic titans might be waiting in the dark, silently steering the motion of galaxies in ways we've yet to imagine. One of the most fleeting yet powerful mysteries in modern astronomy lasts just a fraction of a second: fast radio bursts, or FRB. These incredibly brief cosmic signals pack more energy than the sun emits in decades, vanishing almost as quickly as they appear. First discovered in 2007, these radio pulses originate from galaxies billions of light-years away, traveling across the universe to reach us as faint whispers in telescope data. But their brevity isn't the only puzzle. Some repeat. Unlike most cosmic explosions which flare once and fade, a handful of these bursts have been caught firing off multiple times with no predictable rhythm. The leading suspect behind these enigmatic bursts, magnetars, ultra-dense, highly magnetized remnants of dead stars. When these stellar corpses undergo starquakes or magnetic eruptions, they could unleash a torrent of radio waves powerful enough to reach us across cosmic distances. In 2020, astronomers caught their first break when an FRB erupted from a known magnetar within our own galaxy, adding weight to the theory. But not all bursts fit neatly into this box. Some repeat with patterns too erratic to explain, while others pulse with a precision that borders on artificial. This has led a handful of researchers to entertain an even wilder idea. Could these be the signatures of advanced alien propulsion systems? The notion isn't entirely fringe. Theoretical physicist Avi Loeb has suggested that focused beams powering interstellar light sails might produce similar radio spikes. Yet for every clue, there's a confounding twist. Take FRB 121102, the first repeating burst detected. It fires off like clockwork in a roughly 157-day cycle, active for 90 days, then silent for 67. No known natural phenomenon behaves with such eerie regularity. Other bursts arrive with a Faraday rotation, a telltale twist in their radio waves suggesting they've traveled through an intensely magnetic environment, like the turbulent outskirts of a black hole. Then there's FRB 190523, which arrived with a lower frequency cutoff, hinting it passed through a dense, ionized shroud, possibly the remnants of a supernova or a chaotic star-forming region. The challenge in unraveling FRBs lies in their unpredictability. Unlike supernova or gamma-ray bursts, which announce themselves with fireworks across multiple wavelengths, these radio flashes leave only the faintest fingerprints. Catching one in the act requires telescopes monitoring vast swaths of sky around the clock, waiting for that split-second blip. Even then, pinpointing their origin demands lightning-fast coordination to train other observatories on the spot before the trail goes cold. What makes these bursts so captivating isn't just their mystery, it's what they reveal about the universe's hidden chaos. Each FRB carries imprints of the material it's traveled through, offering a snapshot of the otherwise invisible gas and magnetic fields threading the cosmos. They're cosmic messengers whispering secrets about the spaces between galaxies, the birth and death of stars, and perhaps even realms of physics we've yet to imagine. Whether born from dying stars, alien megastructures, or something even stranger, one thing's certain. In a universe that thrives on the spectacular, fast radio, bursts remind us that sometimes the most extraordinary discoveries come in the blink of an eye. Deep in the outer reaches of our solar system, two robotic explorers, Pioneer 10 and Pioneer 11, were behaving in a way that made scientists double-check their calculations. These hardy spacecraft, launched in the early 1970s, had long completed their primary missions, sailing past Jupiter and Saturn to become the first human-made objects destined to drift among the stars. But as they ventured farther from the Sun, tracking data revealed something odd. Both probes were slowing down slightly more than physics predicted. This tiny discrepancy, just a fraction of a nanometer per second squared, became known as the Pioneer anomaly, a puzzle that would haunt astrophysicists for decades. At first glance, the numbers seemed trivial, but in the precise world of orbital mechanics, even the smallest deviation can hint at something profound. Was it a flaw in our understanding of gravity, an undiscovered force at work in the outer solar system, or perhaps evidence of exotic physics like interactions with dark matter? The anomaly sparked a frenzy of theories, ranging from the plausible to the wildly speculative. Some researchers even revisited Einstein's theory of general relativity, wondering if the probes had stumbled upon a subtle crack in its foundations. Then came the breakthrough. After years of painstaking analysis, scientists realized the answer might be far simpler and far stranger. The Pioneers, powered by radioactive plutonium, were constantly emitting heat. As this thermal radiation bounced off the spacecraft's asymmetrical surfaces, it created a tiny but measurable push, like a car idling with one window slightly open. The effect was minuscule, but over billions of miles, it added up to the exact deceleration observed. Case closed, not quite. While thermal radiation explained most of the anomaly, some researchers argue that a whisper of the original mystery lingers, a residual drift that still defies full explanation. What makes the Pioneer anomaly so captivating isn't just the science, it's the lesson it teaches about how discovery works. Here was a glitch so small it could have been dismissed as noise. Instead, it became a rallying point for curiosity, pushing engineers and physicists to comb through decades-old data, rebuild computer models from scratch, and question assumptions they'd taken for granted. In the end, the pursuit of an answer led to sharper tools, better spacecraft designs, and a deeper appreciation for the hidden complexities of spaceflight. The Pioneers may have solved their own riddle, but their legacy lives on. Every time a spacecraft veers off course by a hair's breadth or a measurement doesn't quite add up, scientists remember, sometimes the universe's greatest secrets hide in the smallest details. And it's in those details, those stubborn, unexplained anomalies, that the next revolution in our understanding might be waiting. The Moon today is a silent, airless world, its surface etched with craters and ancient lava flows. But billions of years ago, it may have harbored a secret that defies its quiet present, a magnetic field. For decades, lunar rocks brought back by Apollo astronauts held clues to this lost chapter in the Moon's history. These samples contain traces of magnetization, evidence that our celestial neighbor once generated its own magnetic shield, much like Earth does today. The puzzle: the Moon is far too small to power a dynamo, the churning core of molten metal that sustains our planet's magnetic field. So how did it happen, and why did it vanish without a trace? One leading theory points to an ancient cosmic dance. Early in its history, the Moon orbited much closer to Earth, and the gravitational pull between the two worlds may have kept the lunar interior in motion. Like stirring a cup of coffee, this tidal heating could have sustained a molten core long enough to generate a temporary dynamo effect. But as the Moon gradually drifted outward, that energy source faded and its magnetic field sputtered out. Supporting this idea, the magnetization in lunar rocks coincides with the period when the Moon was closest to Earth, roughly 3 to 4 billion years ago. Then there's the impact hypothesis, a dramatic alternative. Some researchers argue that colossal asteroid strikes could have supercharged the Moon's core, creating short-lived bursts of magnetic activity. Imagine a hammer striking an anvil. The sheer force of these collisions may have jolted the lunar interior into motion, producing transient fields that left their mark on surface rocks. This would explain why some younger samples show signs of magnetism long after the Moon's dynamo should have died. But critics point out that such events would be sporadic, not the steady, billion-year field suggested by the data. Perhaps the most mind-bending possibility involves external forces. Earth's own magnetic field, far stronger in the past, might have temporarily induced a secondary field in the Moon, like magnetizing a piece of iron held close. Or the solar wind, the stream of charged particles from the Sun, could have interacted with the Moon's crust in ways we don't yet understand, creating illusionary magnetic signatures. What makes this mystery so compelling isn't just the science. It's the way it forces us to rethink planetary magnetism. If a small, geologically dead world like the Moon once had a magnetic field, what other surprises might lurk in the cosmos? Could moons orbiting distant gas giants like Europa or Titan hide similar secrets? The answers could rewrite our understanding of how celestial bodies evolve and what conditions might nurture life beyond Earth. As lunar missions return to the Moon's surface in the coming years, new samples and experiments may finally crack the case. Until then, those magnetized rocks remain silent witnesses to a time when the Moon was anything but inert, a world alive with unseen forces, its history written in the faint echoes of a magnetic whisper. In the afterglow of the Big Bang, the cosmic microwave background radiation that blankets the universe, there's a patch of sky that doesn't belong. Near the constellation Eridanus, a vast and eerie cold spot stretches across the heavens, a region significantly chillier than the rest of the universe's primordial heat signature. This isn't just a minor temperature dip, it's a cosmic anomaly so pronounced that some scientists argue it shouldn't exist at all. The cold spot spans nearly 200 million light-years, a staggering void where the laws of standard cosmology seem to falter. When astronomers first mapped the cosmic microwave background in detail using satellites like WMAP and Planck, this cold spot stood out immediately. The temperature fluctuations in the CMB are typically tiny variations of just 1 part in 100,000. But this region is colder by about 70 microkelvins, a deviation that defies simple statistical chance. Random fluctuations could explain small cold patches, but something this extreme, the odds are astronomically low, somewhere around 1 in 200. So what could create such a bizarre feature in the fabric of the universe? One leading theory suggests the cold spot might be a supervoid, an enormous, nearly empty region of space where matter is strangely scarce. In these cosmic deserts, photons from the CMB lose energy as they traverse the expanding void, a phenomenon known as the integrated Sachs-Wolf effect. The problem: even the largest known supervoids don't come close to explaining the cold spot's intensity. If a void is responsible, it would need to be far larger and emptier than anything we've ever observed, a structure so vast it challenges our understanding of how matter clumps together in the cosmos. Then there's the more radical idea: the cold spot could be a bruise left by a collision with another universe. In the multiverse scenario, where countless bubble universes float in a higher dimensional space, our universe might have bumped into a neighboring one long ago. The energy drained during such a collision could have left behind this anomalous chill, a fingerprint of a reality beyond our own. It's a speculative notion, but for some physicists, the cold spot's extreme properties make it one of the few observable hints that parallel universes might be real. Skeptics, however, argue for less exotic explanations. Instrumental error, statistical flukes, or even undiscovered local foreground effects could be muddying the data. Others propose that the cold spot might be a rare but natural fluctuation in the early universe's density, an outlier in an otherwise uniform cosmos. But every time researchers attempt to model these possibilities, the cold spot resists easy dismissal, lingering as a persistent thorn in the side of cosmological models. What makes this anomaly so fascinating isn't just the scientific debate, it's what the cold spot represents. If it's a supervoid, it forces us to reconsider how structures form on the largest scales. If it's evidence of a multiverse, it could revolutionize our understanding of reality itself. And if it's neither, well, that might be the most exciting possibility of all, a sign that the universe still has secrets we haven't even begun to imagine. As telescopes grow more powerful and simulations more sophisticated, the cold spot remains a beacon for curiosity. It reminds us that even in the most well-studied corners of science, there are still puzzles waiting to be solved, enigmas that might one day rewrite the textbooks. And until we crack this cosmic riddle, that chilly patch near Eridanus will keep drawing our gaze upward, urging us to look deeper and wonder, what else is out there, hidden in the afterglow of creation? In the vast tapestry of cosmic nebulae, those swirling clouds of gas and dust where stars are born and die, most take on familiar shapes, billowing spheres, delicate tendrils, or chaotic explosions frozen in time. Then there's the Red Rectangle Nebula, a structure so geometrically precise it looks less like a celestial object and more like a piece of abstract art. Located about 2,300 light-years away in the constellation Monoceros, this glowing crimson enigma defies every expectation of how stellar debris should behave. Its namesake rectangular shape, framed by luminous rungs that resemble a ladder, is unlike anything else observed in the universe. At the heart of this cosmic oddity lies a dying star, HD 44179, shedding its outer layers in a final act of stellar evolution. Most aging stars expel their material in chaotic, asymmetrical bursts, creating the classic planetary nebulae we're accustomed to seeing. But the red rectangle's symmetry suggests something far stranger at work. The prevailing theory points to an unseen companion, a second star locked in a tight orbit with the primary, sculpting the ejected gas into that unmistakable angular form. As the dying star's winds collide with the gravitational influence of its partner, the result is a phenomenon akin to spinning a garden hose in precise circles, creating a pattern of concentric squares and X-shaped spikes visible in Hubble's stunning images. Yet the mysteries don't stop at its shape. The red rectangle's eerie red glow comes from an unusual mix of hydrocarbons, complex organic molecules that typically shouldn't survive the harsh radiation of space. These compounds, called polycyclic aromatic hydrocarbons, are more commonly found in the sooty aftermath of combustion on Earth, not floating in the void around a star. Their presence hints at chemical processes we've yet to fully understand, possibly catalyzed by shock waves or hidden magnetic fields in the nebula's intricate structure. Even more puzzling, spectroscopic analysis reveals spikes of emission lines dubbed the red rectangle bands, a fingerprint of light that still lacks a definitive explanation despite decades of study. What makes this nebula so captivating isn't just its defiance of natural chaos. It's the window it offers into the universe's hidden artistry. The red rectangle challenges our assumptions about how stars die, how matter organizes itself in space, and even how complex molecules form in the most unlikely environments. It's a reminder that the cosmos has a flair for the unexpected, crafting structures so precise they seem almost deliberate. As astronomers continue to probe its secrets, the red rectangle stands as a testament to the universe's creativity, a place where geometry, chemistry, and stellar physics collide in ways we're only beginning to unravel. Whether it's the unseen hand of a binary companion, the alchemy of rare molecules, or some undiscovered force at work, one thing is clear. In a universe full of beautiful anomalies, the red rectangle is a masterpiece without equal. When you think of storms, you probably imagine swirling cyclones or spiraling hurricanes, chaotic, organic shapes governed by the wild dance of wind and pressure. But Saturn has a different idea. At its north pole, a perfect hexagon, a six-sided geometric storm, spins with clockwork precision, each side stretching nearly 9,000 miles across. This isn't some fleeting atmospheric quirk. It's a permanent fixture, first spotted by Voyager in the 1980s and still raging decades later. How does a planet known for its elegant rings produce something so starkly, impossibly geometric? Earth's storms are messy by comparison. Our hurricanes form over warm ocean waters, fueled by rising heat and the Coriolis effect, twisting into spirals that eventually lose steam over land. Even Jupiter's Great Red Spot, a storm centuries old, follows the rules of fluid dynamics, a turbulent oval churning in the gas giant's atmosphere, but Saturn's hexagon defies those rules. It's not just a shape, it's a rigid, towering structure that extends hundreds of miles into the planet's atmosphere, with winds screaming at over 200 miles per hour along its edges. And unlike Earth storms, which dissipate or drift, this hexagon has held its form for at least 40 years, maybe longer. Scientists have scrambled to explain it. One leading theory points to atmospheric jets, fast-moving streams of gas interacting with Saturn's rotation. In lab experiments, spinning liquids can form polygonal shapes under the right conditions, hinting that the hexagon might be a standing wave, frozen in place by the planet's rapid rotation and the tug of opposing winds. But here's the catch. No model perfectly replicates the hexagon's stability or sharp angles. Earth's atmosphere is too thin, too layered to sustain such a structure. Saturn's deep, hydrogen-rich skies might be the key, acting like a cosmic fluid dynamics lab on a planetary scale. Then there's the question of depth. Recent data from the Cassini spacecraft revealed something startling. The hexagon isn't just a surface feature. It plunges deep into Saturn's atmosphere, possibly anchored by processes far below the clouds. Some researchers speculate that Saturn's internal heat, rising in colossal convection currents, could be shaping the hexagon from within, like an invisible hand molding the storm into its uncanny form. Others wonder if the planet's magnetic field plays a role, though no one's quite sure how. What makes this anomaly so mesmerizing isn't just the defiance of physics, it's the reminder that nature's rulebook is far thicker than we realize. On Earth, hexagons appear in beehives and basalt columns, products of efficiency or cooling stress. But on Saturn, they're writ large across the sky, a cosmic billboard advertising how little we truly understand about the universe's capacity for order amid chaos. As future missions probe deeper into gas giants, the hexagon stands as a beacon of the unknown, a shape that shouldn't exist, yet stubbornly does. Whether it's a footnote in atmospheric science or a clue to deeper planetary mysteries, one thing's certain: Saturn isn't just a jewel in the solar system. It's a puzzle waiting for the next curious mind to unlock its secrets. The universe holds a cosmic accounting error, one so glaring it's baffled astronomers for decades. If you tally up all the ordinary matter, the stars, planets, gas, and dust that make up everything we can see, it accounts for barely half of what the Big Bang's leftover radiation says should be there. This is the missing baryon problem. A staggering 40 to 50% of the universe's normal matter has seemingly vanished without a trace. The kicker: we're not even talking about dark matter here. This is the stuff we know exists: protons, neutrons, electrons, the building blocks of galaxies, of life itself. So where did it all go? For years, scientists suspected this missing matter might be hiding in plain sight, woven into the fabric of the cosmos in a form too faint to detect. Enter the WIM, the warm, hot intergalactic medium. Picture this: vast, thread-like filaments of superheated gas stretching between galaxies like a cosmic spiderweb. These filaments, predicted by simulations, are so diffuse they're nearly invisible. The gas within them is scorching, up to 10 million degrees, but so thinly spread that a cubic meter of it might contain just a single atom. That's why traditional telescopes miss it. The WIM doesn't glow brightly enough in visible light or X-rays to stand out against the noise of the universe. But astronomers are resourceful. In recent years, they've turned to clever workarounds, like using distant quasars, the blazing cores of ancient galaxies, as cosmic flashlights. When light from a quasar passes through these filaments, trace elements like oxygen get ionized, leaving faint absorption lines in the quasar's spectrum. It's like spotting a fingerprint on a foggy window. Slowly, painstakingly, these observations have begun to reveal the WIM hidden architecture. The European Space Agency's XMM Newton and NASA's Chandra X-ray Observatory have even detected whispers of this elusive matter by catching the faint X-ray glow emitted when WIM gas smashes into galactic clusters. Still, these detections account for only a fraction of the missing baryons. Some theorists suggest the rest could be lurking in even stranger places, perhaps as rogue black holes, ultra-faint dwarf galaxies, or even dispersed in vast, cold reservoirs between galactic superclusters. Others wonder if our models of the early universe need tweaking, or if some of this matter exists in exotic states we've yet to imagine. The challenge is monumental, but the stakes are higher than just solving a puzzle. This missing matter isn't just academic. It's the very material that forms the backbone of galaxies, the scaffolding of the cosmos. What makes this hunt so thrilling isn't just the mystery, it's the detective work. Every new telescope, every innovative observation technique brings us closer to balancing the universe's books. And when we finally account for those last stray baryons, it won't just close a gap in our equations. It'll rewrite our understanding of how the cosmos builds itself, one atom at a time. Some regions of space are crowded with galaxies, bustling metropolises of stars and dust. Then there's the Boötes Void, a cosmic ghost town so vast and empty it defies comprehension. Stretching 330 million light-years across, this enormous spherical desert in the constellation Boötes contains almost nothing. To put that in perspective, if the Milky Way were placed at its center, the nearest galaxy would be tens of millions of light-years away. For scale, our own local group of galaxies fits comfortably inside a space just 10 million light-years wide. The Boötes Void isn't just a gap, it's a staggering absence where the universe forgot to put anything at all. When astronomers first mapped this void in the 1980s, they assumed it must be an observational error. The odds of nature carving out such a perfect, near-empty sphere seemed impossibly low. Yet deeper surveys confirmed the impossible. Fewer than 60 galaxies lurk in this expanse where standard models predict thousands. If the universe's matter were distributed evenly, a void this size simply shouldn't exist. So what could have scooped out such an unimaginably large pocket of nothingness? One theory points to the violent aftermath of the Big Bang. Tiny quantum fluctuations in the early universe stretched to cosmic scales, leaving behind overdense regions where galaxies clustered, and underdense ones like the Boötes void where matter was stretched too thin to form structures. It's the cosmological equivalent of dough rising unevenly, with some bubbles expanding into vast empty cavities. But even this explanation struggles to account for the void's sheer scale. Some researchers speculate that multiple smaller voids might have merged over billions of years, creating one colossal emptiness through a kind of cosmic erosion. Then there's the more provocative idea: what if the void isn't empty at all, but filled with something we can't see? Dark energy, the mysterious force accelerating the universe's expansion, might operate differently in these regions, pushing matter apart more aggressively. Or perhaps the void is a battleground where dark matter, the invisible glue holding galaxies together, somehow failed to clump as expected. A handful of theorists have even floated the notion of a universe in a universe, where the Boötes void marks the imprint of a long-ago collision with another space-time bubble. But not everyone's convinced the void is special. Skeptics argue it might be a statistical fluke, a rare but natural fluctuation in the cosmic web. After all, if you roll the dice enough times, eventually you'll land on a string of unlikely outcomes. The real test will come as telescopes map more of the universe in finer detail. If other voids this size turn up, it could rewrite our understanding of how large-scale structures form. What makes the Boötes void so haunting isn't just its emptiness, it's the way it forces us to question the universe's fundamental rules. Is it a cosmic accident or a sign of physics we've yet to discover? For now, the void keeps its secrets, a silent reminder that even in a universe teeming with galaxies, sometimes the most profound mysteries lie in the spaces between. In the afterglow of the Big Bang, the cosmic microwave background should be random, a perfectly uniform sea of primordial light, peppered with tiny temperature fluctuations scattered in no particular pattern. But when scientists mapped this ancient radiation with satellites like WMAP and Planck, they stumbled upon something that sent chills through the astrophysics community. Dubbed the axis of evil, this bizarre anomaly reveals an eerie alignment. The CMB's fluctuations aren't random at all. Instead, they appear to line up with the plane of our solar system, as if the universe itself were whispering that we occupy a strangely privileged place in the cosmos. At first glance, this sounds like a statistical fluke. The cosmic microwave background is a snapshot of the universe when it was just 380,000 years old, frozen in time as the first atoms formed. Those faint temperature variations, hot spots and cold spots, are the seeds of all future galaxies, distributed by quantum fluctuations stretched across space by inflation. According to standard cosmology, their distribution should be isotropic, meaning no direction is special. Yet the data stubbornly refuses to comply. The largest scale fluctuations align along an axis that eerily traces the ecliptic, the same plane in which Earth and the other planets orbit the Sun. The odds of this happening by chance, less than 1 in 1,000. Some scientists argue this points to a fundamental flaw in our understanding of the early universe. If the CMB's structure is linked in any way to our solar system's orientation, it could mean the cosmos isn't as uniform as we thought, a direct violation of the cosmological principle, the bedrock assumption that the universe looks the same in all directions on large scales. Others speculate about even wilder possibilities. Could the axis of evil be evidence of a pre-Big Bang universe imprinting its structure onto ours? Or might it hint at undiscovered physics, like a long-range force tying matter across cosmic distances in ways Einstein's relativity never predicted? Then there's the more unsettling idea. What if it's not the universe that's strange, but our measurements? Critics suggest the alignment could stem from unaccounted for biases in how we observe the CMB. Dust in our own galaxy, the solar system's motion through space, or even subtle instrumental errors might be warping the data. Yet after years of meticulous analysis, no single systematic error fully explains the signal. The Planck mission, with its unprecedented precision, only deepened the mystery, confirming the anomaly was real, not some artifact of imperfect technology. What makes the axis of evil so provocative isn't just the scientific debate, it's the philosophical weight behind it. For centuries, humanity has struggled to shed the illusion that we're somehow central to the universe. Copernicus dethroned Earth from the center of the solar system. Hubble revealed our galaxy as just one among billions, yet here we are, facing an anomaly that seems, against all odds, to whisper that maybe, just maybe, there's something special about our corner of spacetime after all. Until the riddle is solved, the axis of evil lingers as a cosmic taunt, challenging us to dig deeper. Whether it's an artifact of observation, a flaw in our models, or a genuine crack in the cosmological principle, one thing's certain: the universe still has cards it hasn't shown us. And in those cards might lie answers or even bigger questions that reshape our place in the grand scheme of everything. For centuries, stargazers have marveled at a faint, ghostly glow that stretches across the pre-dawn or post-sunset sky, a phenomenon called the zodiacal light. This ethereal pyramid of light, best seen in pristine dark sky locations, comes from sunlight scattering off countless dust particles orbiting the sun in the same plane as the planets. But when modern astronomers tried to quantify this dust, they hit a cosmic snag. The observed glow is far brighter than it should be. According to our best models, the known population of asteroids and comets, the usual suspects for supplying interplanetary dust, falls short by a staggering 90%. So where's all this extra dust coming from? One leading theory points to a hidden reservoir of asteroids lurking closer to the sun than we've been able to observe. Dubbed volcanoids, these hypothetical rocky bodies could orbit in a blind spot between Mercury and the sun, where intense solar glare makes them nearly impossible to detect with current telescopes. Over billions of years, collisions among these unseen asteroids could have generated vast amounts of dust, explaining the excess glow. But despite decades of searching, no definitive volcanoid population has been found. Even if they exist, their numbers likely couldn't account for the full discrepancy. Another possibility involves interstellar interlopers. Recent studies suggest up to half the zodiacal dust might not be homegrown at all. It could be alien grit, drifting into our solar system from the wider galaxy. Observations from NASA Juno spacecraft revealed a population of dust grains moving at speeds too high to be bound by the sun's gravity, hinting at an external origin. If true, this interstellar dust would act like cosmic sandpaper, constantly sanding down our local asteroids and comets, producing even more reflective debris than expected. Yet the mystery deepens when we consider the dust's distribution. Some infrared surveys reveal bizarre clumps and asymmetries in the zodiacal cloud, features that defy the smooth, even spread predicted by standard models. Could gravitational interactions with Jupiter or Saturn be herding dust into dense pockets? Or are we seeing the aftermath of recent, unseen collisions between massive asteroids? The answer might lie in upcoming missions like ESA's Comet Interceptor, designed to study pristine comets and their dust trails in unprecedented detail. What makes this cosmic dust dilemma so fascinating isn't just the missing mass, it's what it reveals about our solar system's hidden dynamics. Every speck of zodiacal dust is a fossil, tracing the violent history of asteroids, the subtle tug of planets, and perhaps even the whispers of distant stars. Whether the solution lies in unseen asteroids, interstellar visitors, or something even stranger, one thing's clear: even in our own celestial backyard, the universe keeps surprising us with puzzles waiting to be solved. Mars should be a dead world, frozen, barren, and chemically inert. Yet something on the red planet is breathing. Over the past 2 decades, multiple missions have detected fleeting whiffs of methane in its thin atmosphere, a gas that on Earth is almost exclusively tied to biological activity. These tantalizing spikes, sometimes vanishing as quickly as they appear, have sparked one of the most heated debates in planetary science. Is Mars hiding microbial life beneath its rusty surface, or are we seeing the fingerprints of an entirely different kind of mystery? The saga began in 2003 when the European Space Agency's Mars Express orbiter first reported traces of methane hovering over certain regions. Since then, NASA Curiosity rover has confirmed these detections from the ground, sniffing out methane concentrations that occasionally spike tenfold before dissipating within weeks. The pattern defies easy explanation. If the gas were seeping from geological sources like underground water rock reactions or ancient methane clathrates, we'd expect steady, predictable releases. Instead, the methane behaves like a phantom, appearing suddenly in Gale Crater, then disappearing before scientists can trace its origin. What makes this enigma so electrifying is methane's fragility. Solar radiation and chemical reactions should break it apart within a few hundred years, meaning any methane we detect today must have been produced recently. On Earth, 95% of atmospheric methane comes from living organisms, from microbes in wetlands to the digestive tracts of cattle. Could Martian microbes hidden in briny aquifers or deep underground be responsible? Some researchers point to terrestrial analogues like methanogens, extremophiles that thrive in oxygen-free environments similar to Mars' subsurface. These organisms produce methane as a byproduct of their metabolism, raising the tantalizing possibility that Curiosity's instruments might be picking up the faint exhaust of an alien biosphere. But before we rewrite biology textbooks, other explanations vie for attention. Serpentinization, a process where water reacts with olivine-rich rocks, can produce methane abiotically. Mars' volcanic past might have left pockets of heat and liquid water deep underground, driving these reactions even today. Then there's the comet hypothesis. Perhaps ancient impacts delivered methane-rich ices that occasionally sublimate when disturbed. Even more puzzling, the ExoMars Trace Gas Orbiter, a mission specifically designed to study Martian methane, has repeatedly failed to confirm Curiosity's ground-level spikes from orbit, leaving scientists scrambling to reconcile the contradictory data. The plot thickens when you consider atmospheric dynamics. Methane might get trapped under layers of dust or ice, only released when temperature changes fracture the seals. Some models suggest seasonal variations or even daily cycles could concentrate the gas in ways we're only beginning to understand. Imagine methane trickling up through porous rock, pooling in underground caverns, then erupting in brief puffs when pressure builds, a geological sneeze echoing across an otherwise silent planet. What makes the Mars methane mystery so gripping isn't just the search for life. It's the reminder that even our closest planetary neighbor still guards its secrets fiercely. Every new detection, every contradictory measurement, forces us to question our assumptions about how worlds evolve, what processes shape their chemistry, and where life might find a foothold in the cosmos. Until we drill deeper, until we land a mission capable of distinguishing biological from geological fingerprints, Mars will keep its cryptic methane whispers just out of reach, teasing us with possibilities that dance between the mundane and the revolutionary. For now, the mystery lingers like a faint scent on the wind, daring us to follow it to its source. Whether it leads to subterranean microbes or a previously unknown geochemical process, one thing's certain: Mars isn't as dead as it seems. And that realization alone makes every whiff of methane a cosmic cliffhanger, a story still being written in the thin, cold air of another world. Venus has long been painted as Earth's toxic twin, a scorching, acidic hellscape where nothing could survive. But in September 2020, that narrative cracked open. a team of astronomers made an explosive announcement. They detected phosphine gas in Venus's upper clouds, a molecule that on Earth is almost exclusively produced by living organisms or human industry. The implications were staggering. Floating 50 kilometers above the planet's crushing surface, where temperatures and pressures are eerily Earth-like, could there be microbes thriving in the sulfuric acid-laced skies? The discovery sent shockwaves through the scientific community. Phosphine, a simple compound of 1 phosphorus and 3 hydrogen atoms, shouldn't last more than minutes in Venus's corrosive atmosphere unless something or someone is actively replenishing it. On our planet, anaerobic bacteria in swamps and animal guts churn it out as a byproduct of their metabolism. No known non-biological process on Venus, from volcanic eruptions to lightning strikes, could plausibly generate the concentrations observed. The data collected by the James Clerk Maxwell Telescope in Hawaii and later corroborated by the Oumuamua Array in Chile seem to point to one electrifying possibility: the first potential evidence of life beyond Earth. But in science, extraordinary claims demand extraordinary scrutiny, and the pushback was swift. Skeptics questioned the data processing, arguing that the faint phosphine signal might be a false positive caused by sulfur dioxide, a common Venusian gas with a similar spectral fingerprint. Others pointed to unknown atmospheric chemistry, suggesting high-altitude reactions or even meteorite dust could be producing phosphine through exotic pathways we haven't yet imagined. By 2021, some teams analyzing the same datasets found no trace of the gas at all, deepening the controversy. Then came the alternative explanations. Some researchers proposed that volcanic eruptions, though rare on Venus, might belch phosphorus-rich compounds into the atmosphere, where sunlight or lightning could transform them into phosphine. Others floated the idea of abiotic photochemistry, a complex chain of reactions driven by Venus's intense solar radiation. Even more radical was the suggestion that micrometeorites constantly raining down on the planet's atmosphere might carry phosphorus that reacts with hydrogen in unexpected ways. Yet the most tantalizing thread refused to snap: the sheer difficulty of explaining the phosphine without biology. Venus's clouds, once written off as sterile, are now the subject of revived interest. Recent studies reveal patches of unexplained dark streaks in the atmosphere, possibly composed of particles that absorb ultraviolet light, a phenomenon some compare to algal blooms on Earth. Could these be the very organisms producing the gas? The debate is far from settled, but one thing is undeniable: Venus just got a lot more interesting. Whether the phosphine is a mirage, a geological fluke, or the whisper of life itself, it's forced us to rethink what's possible in our own cosmic backyard. Missions like NASA Da Vinci and ESA's Envision, set to probe Venus's atmosphere in the coming decade, may finally crack the case. Until then, the phosphine mystery lingers, a smoky signal in the clouds daring us to look closer. Beyond the orbit of Neptune, where sunlight dwindles to a faint glimmer, the solar system doesn't just fade quietly into the dark. Instead, it ends with a cosmic slam of the door, a boundary so abrupt astronomers call it the Kuiper Cliff. Out in the frigid reaches of the Kuiper Belt, a vast ring of icy debris left over from the solar system's birth, thousands of objects circle the sun in lazy orbits. But past 50 astronomical units, about 7.5 billion kilometers out, this celestial junkyard suddenly empties. It's as if an invisible line were drawn, beyond which almost nothing dares to tread. The drop-off is so sharp, so unnatural, that it defies everything we know about how planetary systems form. So what's lurking out there, carving this invisible edge into our cosmic backyard? One leading theory points to an unseen ninth planet, not Pluto, but something far more massive. This hypothetical world, sometimes called Planet 9, could be 10 times heavier than Earth, lurking hundreds of astronomical units away in a tilted, elongated orbit. Its gravity would act like a shepherd, hurling Kuiper belt objects inward or kicking them out of the solar system entirely, leaving behind that eerie no man's land beyond 50O. Computer simulations show this could explain not just the cliff, but also the peculiar clustered orbits of some distant objects like Sedna, the Catch. After years of searching, no telescope has yet spotted this phantom planet. If it exists, it's a master of hiding, reflecting so little sunlight it's practically invisible against the blackness of space. But Planet 9 isn't the only suspect. Another possibility rewinds the clock 4.5 billion years to when the solar system was a chaotic construction zone. Back then, the young sun didn't orbit alone. It was likely born in a crowded stellar nursery alongside hundreds of sibling stars. One of these siblings, brushing too close, could have stolen away the outer Kuiper belt's material in a gravitational tug of war, leaving behind only the truncated disk we see today. Alternatively, the Sun itself might have once had a second, smaller companion star, a common setup in binary systems that later drifted away or was captured by another passing star, destabilizing the outer solar system in the process. Yet not all explanations require dramatic interventions. Some scientists argue the Kuiper cliff could be an illusion, an observational artifact caused by the difficulty of spotting faint, distant objects. After all, the farther out you go, the dimmer Kuiper belt objects become, and the harder they are to detect. But recent surveys, equipped with ultra-sensitive instruments like the Subaru telescope, have turned up empty-handed where they should have found hundreds more objects. The absence seems real, and that makes it all the more baffling. What makes the Kuiper cliff so intriguing isn't just the mystery of what's out there, it's what it reveals about the solar system's hidden history. Whether it's a lurking super-Earth, a long-lost stellar encounter, or something even stranger, this abrupt boundary whispers of forces shaping our cosmic neighborhood in ways we're only beginning to grasp. Every empty patch of sky beyond 50O is a question mark, a challenge flung down to astronomers. Keep looking, because the solar system's final frontier still has secrets to spill. For billions of years, the Milky Way and Andromeda have been locked in a slow-motion cosmic dance, destined to collide in one of the universe's most spectacular mergers. Current estimates suggest this galactic pileup will happen in about 4 billion years, but there's a problem. The two galaxies are rushing toward each other faster than our models predict, as if some unseen hand is pressing the accelerator. Measurements show Andromeda approaching at nearly 300 kilometers per second, roughly 50 kilometers per second faster than expected given the gravitational pull of visible matter alone. This discrepancy isn't just a rounding error. It's a clue that our understanding of the local universe might be missing something fundamental. One leading suspect is dark matter, the invisible scaffolding thought to make up 85% of the universe's mass. If our models of its distribution are off, even slightly, it could explain the unexpected speed. Computer simulations based on standard cosmology predict dark matter should be spread relatively smoothly through space, forming vast halos around galaxies. But what if Andromeda's halo is denser or more extended than we've assumed? That extra gravitational pull would yank the Milky Way toward it faster, like an invisible rope tightening between them. Alternatively, the two galaxies might be embedded in a larger, unseen structure, a filament of dark matter weaving through the local cosmic web, adding an extra tug we haven't accounted for. Then there's the wild card of local group dynamics. The Milky Way and Andromeda aren't the only players in this gravitational game. Dozens of smaller galaxies, including the Triangulum Galaxy, orbit within our neighborhood, their collective mass subtly influencing the larger galaxy's trajectories. Some astrophysicists suggest these smaller satellites could be funneling dark matter into streams or clumps, warping the gravitational landscape in ways we're only beginning to map. Throw in the possibility of past galactic collisions, Andromeda's distorted disk hints at a violent history, and the math gets even messier. the implications ripple far beyond timing a far future collision. If our predictions are wrong, it could mean we've misjudged the balance of dark and visible matter in our cosmic backyard. Upcoming telescopes like the Vera Rubin Observatory and the Euclid space mission aim to shed light on these shadowy discrepancies by mapping the distribution of matter with unprecedented precision. Until then, the Andromeda anomaly stands as a humbling reminder that even in our own galactic neighborhood, the universe still holds surprises. Whether it's hidden matter, overlooked dynamics, or something even stranger at work, one thing's clear: the cosmos doesn't follow a script. Every unexpected measurement, every stubborn deviation is an invitation to look deeper and to wonder what else we might have missed in the grand story of our unfolding universe. And when these two galaxies finally meet, the dance won't be a catastrophic crash, but a slow, majestic swirl, stars passing like ships in the night, their paths bending but rarely colliding in the vast emptiness of space. The real spectacle will unfold over billions of years as gravity weaves their stars, gas, and dark matter into a single, luminous giant, a new galaxy born from the embrace of two cosmic titans. Until then, their silent, speeding approach keeps us guessing and reminds us that even the most certain-seeming celestial events can carry mysteries of their own. Among the countless galaxies dotting the cosmos, most follow familiar blueprint spirals with elegant arms, ellipticals like glowing clouds, or messy irregulars shaped by collisions. Then there's Hoag's object, a celestial oddity so perfect it seems almost artificial. Floating 600 million light-years away in the constellation Serpens, this galaxy is a stunning golden ring of young, blue stars encircling a core of ancient red suns with nothing but darkness between them. No spiral arms branch outward, no dusty lanes disrupt its symmetry, just a luminous halo floating around a central sphere like a cosmic bullseye. It defies every expectation of how galaxies form and evolve, leaving astronomers to wonder, how does something so flawless come to exist? Typical ring galaxies usually form through violent collisions, where a smaller galaxy punches through the center of a larger one, sending shockwaves that trigger star formation in a circular ripple. But Hoag's object shows no signs of such trauma. There's no debris, no distorted remnants of a past impact, just eerie, pristine perfection. Some researchers suggest it could be the product of a rare instability, where a galaxy's own internal dynamics caused its disk to expand outward while the core remained intact. Others propose an even stranger idea. Perhaps it's the aftermath of an ancient accretion event, where a vast cloud of intergalactic gas was captured and funneled into a ring by the galaxy's gravity, igniting waves of starbirth without the mess of a collision. What makes Hoag's object especially tantalizing is the glimpse it offers into galactic adolescence. The vibrant blue stars in its ring are likely less than 100 million years old, cosmic infants compared to the ruddy giants in its core. This stark contrast suggests the galaxy experienced two distinct epochs of star formation, with the ring's birth occurring far later than the core's. Was it triggered by an unseen interaction, or does this galaxy simply march to the beat of its own drum? Adding to the intrigue, astronomers have spotted another, fainter ring galaxy lurking even farther in the background, a cosmic coincidence that deepens the mystery of how such rarities emerge. Theories continue to swirl, but one thing's certain: Hoag's object is a reminder that the universe refuses to be pigeonholed. For every rule governing galactic evolution, there's an exception floating in the void, daring us to rethink our assumptions. Whether it's a relic of forgotten collisions, a self-made anomaly, or something entirely beyond our current understanding, this celestial enigma stands as a testament to the cosmos' boundless creativity. A single, perfect ring spinning silently against the dark, waiting for us to unravel its secrets. The way galaxies spin shouldn't make sense. According to the laws of gravity, stars orbiting on the outer edges of spiral galaxies should move slower than those near the center, just like planets farther from the Sun, take longer to complete their orbits. But when astronomers first measured galaxy rotation curves in the 1970s, they found something bizarre. Stars at the fringes were racing just as fast as those near the core. It was as if invisible hands were gripping every galaxy, spinning them like solid plates against the pull of gravity. This cosmic mismatch between prediction and observation became one of the strongest clues that the universe is filled with something we can't see, dark matter. At first, scientists scrambled to explain the anomaly with known physics. Maybe interstellar gas or faint stars were adding unseen mass, but detailed calculations revealed the truth. To account for those flat rotation curves, galaxies would need up to 10 times more matter than what's visible. This missing mass couldn't be ordinary atoms. It had to be something that doesn't interact with light at all, a shadowy substance permeating every galaxy like an invisible scaffold. Today, we call this elusive material dark matter, and its gravitational fingerprints are everywhere, in the way galaxies cluster, how light bends around them, and even how the universe itself evolved after the Big Bang. Yet dark matter isn't the only possible explanation. A small but vocal group of physicists champions an alternative, modified Newtonian dynamics, or MND. This radical idea suggests that gravity behaves differently on galactic scales than Newton or Einstein predicted. Instead of invoking unseen matter, MND tweaks the equations of motion so that stars in the outer reaches of galaxies experience a subtle boost in gravitational pull, keeping them whipping around faster than expected. Proponents point to oddball galaxies like NGC 1052, where rotation curves align neatly with MND predictions without requiring any dark matter at all. The debate between dark matter and MND isn't just academic, it cuts to the heart of how we understand the cosmos. Dark matter fits neatly into our models of cosmic evolution, helping explain everything from the large-scale structure of the universe to the afterglow of the Big Bang. But it's also frustratingly elusive. Despite decades of searching, no direct detection experiment has definitively captured a dark matter particle. MND, meanwhile, elegantly solves the rotation curve puzzle without hidden substances, but struggles to account for other evidence, like the gravitational lensing seen in galaxy clusters. What makes this mystery so compelling is the way it forces us to question fundamental assumptions. Are we missing a particle that makes up most of the universe's matter? Or do we need to rewrite the laws of gravity themselves? The answer might lie somewhere in between, perhaps a blend of unseen matter and subtle tweaks to physics we've yet to discover. Until then, every spinning galaxy serves as a cosmic reminder. The universe still holds profound secrets waiting just beyond the edge of what we can see. The Hubble constant, the rate at which the universe expands, should be one of the most straightforward numbers in cosmology. Yet this single value has sparked one of the fiercest debates in modern astronomy, a stubborn discrepancy between how fast we think the universe is growing and how fast we measure it. On one side, the cosmic microwave background, the afterglow of the Big Bang, suggests an expansion rate of about 67 kilometers per second per megaparsec. On the other, observations of nearby stars and supernova peg it closer to 73. That 6-kilometer gap might sound trivial, but after decades of increasingly precise measurements, it refuses to close. This isn't just a rounding error, it's a full-blown crisis dubbed the Hubble tension, and it might be the universe's way of telling us our understanding of physics is incomplete. At the heart of the conflict lies a tale of two methodologies. The first approach, championed by the Planck satellite, reconstructs the expansion rate by studying the cosmic microwave background's faint temperature fluctuations. These primordial ripples encode the universe's early conditions, allowing cosmologists to extrapolate forward using well-tested theories of dark matter and dark energy. The second method skips the theory and measures expansion directly by tracking the distances and velocities of nearby celestial objects, Cepheid variable stars. whose predictable brightness fluctuations act as cosmic yardsticks, and Type Ia supernova, whose uniform explosions serve as standard candles. The problem: these two gold standard techniques refuse to agree, even as their margins of error shrink to razor-thin levels. Skeptics initially blamed calibration issues. Could Cepheid distance measurements be systematically off? Perhaps interstellar dust is subtly dimming supernova, tricking us into overestimating their distances. But as astronomers cross-checked with independent probes, gravitational lensing time delays, tidal disruption events, even the vibrations of red giant stars, the tension only worsened. Each new dataset seemed to split the difference, or worse, side decisively with one camp over the other. The likelihood that this is all due to measurement errors now stands at less than 1 in a million. The universe, it seems, is genuinely misbehaving. This leaves physicists with a thrilling, if unsettling, possibility. We might need new physics to settle the score. One leading contender is early dark energy, a hypothetical force that briefly surged during the universe's first few 100,000 years, tweaking the CMB's signature in ways that throw off our extrapolations. Another radical idea suggests dark energy isn't constant but evolving, growing stronger or weaker over time in ways we've yet to model. There's even speculation that we're seeing hints of extra neutrino species or exotic matter interactions, particles beyond the standard model, quietly tilting the cosmic scales. Yet the most profound implication isn't just about fixing a number, it's about humility. The Hubble tension forces us to confront how little we truly grasp about the cosmos's inner workings. Are we missing a fundamental ingredient in the universe's recipe? Or is this discrepancy a breadcrumb trail leading to a deeper truth, a crack in the foundation of cosmology itself? With next-generation telescopes like the Vera Rubin Observatory and the Nancy Grace Roman Space Telescope set to unleash torrents of new data, we may soon find out. Until then, the Hubble tension stands as both a puzzle and a promise, proof that even our best theories are works in progress and that the universe still has secrets left to reveal. From unexplained radio bursts to galaxies spinning against the laws of physics, these 25 cosmic anomalies remind us that the universe thrives on mystery. Each one, whether it's Saturn's impossible hexagon, the ghostly whispers of Martian methane, or the Great Attractor's hidden pull, challenges our understanding, forcing scientists to rethink, revise, and sometimes rewrite the rules. These aren't just oddities, they're cosmic breadcrumbs leading us toward discoveries we haven't even imagined yet. Think about it. Every time we've stumbled upon a phenomenon that defies explanation, it's sparked revolutions in science. The wow signal made us listen harder to the cosmos. The Hubble tension might reveal gaps in our grasp of reality itself. And who knows, the next anomaly we uncover could be the key to unlocking dark matter, proving parallel universes, or even finding life beyond Earth. That's the beauty of the unknown. It doesn't just stump us, it pushes us to dig deeper, build better telescopes, and ask bigger questions. So let's keep wondering. Let's keep staring at the night sky with the same awe that drove Galileo and Hubble. Whether your team, alien megastructure for Tabby's star, or convinced the Kuiper Cliff hides a hidden planet, your curiosity is what drives this journey forward. Drop your favorite anomaly in the comments. Was it the red rectangle's eerie geometry or the spine-tingling possibility of Venusian life? Let's geek out together. And if you're craving more cosmic mysteries, hit subscribe. The universe isn't done surprising us, and neither are we. From black hole paradoxes to time-bending quasars, there's always another enigma waiting just beyond the edge of our understanding. So stay curious, stay skeptical, and remember, the weirdest discoveries often start with a simple question. What's your big cosmic what if? The next chapter of the universe's secret starts with you.